Okay, so thank you very much for giving me the opportunity to talk. This BTBB is a famous short coming from consecutive extension. Last year, Professor Suzuki gave a very interesting talk about evolution, in which BTBB means consecutive binary, ternary, binary, and once again binary extension. So he also pointed at the importance of this particular sequence in knot theory and mathematics and language theory and probably in many other fields. So I'm referring to this as some interesting point to consider. Okay, the references here we have several papers by Professor Suzuki, Ławrynowicz, and also some paper of 2005 of Kosaka and Suzuki on iteration dynamical systems of discrete Laplacians and evolution of extinct animals. Also, there was a paper, but lost paper, nobody can find it anymore, but there was a student of Professor Suzuki who did something in that field and showed some interesting computer simulations. I have them in my presentation, but the paper somehow is lost. So we cannot, unfortunately, give the good address. In mathematics, the discrete Laplace operator is an analog of the continuous Laplace operator, defined so that it has the meaning on a graph or a discrete grid. In graph theory, Laplacian matrix, also called the graph Laplacian, admittance matrix, Kirchhoff matrix, or discrete Laplacian, is a matrix representation of the graph, one of the representations. In physics, the discrete Laplace operator occurs in problems such as the Ising model and loop quantum gravity, as well as in the study of discrete dynamical systems. It is also used in numerical analysis as a replacement for the continuous Laplace operator. Okay, so common applications of discrete Laplace operator are image processing, where it is known as the Laplace filter. You can see here on the right the effect of application of Laplacian filter. It makes kind of a drawing out of a picture. In machine learning for clustering and semi-supervised learning on neighborhood graphs as well, and there are many other fields. So, what is Laplacian matrix in graph theory? For simple graphs, the more general definition is the following: we have graph, some number of vertices and some number of edges, and a function from vertices to real numbers, and not real numbers. This is a function of the vertices taken values in a ring. So it doesn't have to be real numbers. Could be a ring. So it could be a ring of, for example, Z2, Z4, Z5, whatever. It could be integer modular ring. Then the discrete Laplacian acting on phi is defined by Laplacian on V is sum over all the vertices whose distance between U and V equal 1. So phi of V minus phi of W. So D of WV is simply distance between vertices V and W. So it is sum over the nearest neighbors of the vertex. So for a simple graph, the Laplacian matrix is something like L minus dA, where D is degree matrix and A is adjacency matrix. So it's something very, very simple and natural. And of course, we have Laplacian defined also for not simple graphs, for directed graphs, for weighted graphs, for any kind of graphs. Sometimes you normalize and you do a lot of tricks depending on what you want to obtain. I would like to mention Laplacian matrix, a random walk normalized Laplacian, which is quite nice because some people are very interested in random walks. So the elements are given by, elements of this matrix are given by just 1 or 0 or -1 over degree of V. So if the degree is very big, so it's kind of tamed. What does it come from? It comes from the fact that this matrix is simply I minus P, where P is D plus A, whatever. This is the degree matrix plus adjacency matrix. Is simply the transition matrix of a random walker on the graph, assuming a non-negative weights of the edges. For example, let EI denote the I standard basis vector, then X equal EIP is a probability vector representing distribution of a random walker's locations after taking a single step from vertex I. That is, Xj is P, represents a walk from Vi to Vj. More generally, if the vector X is a probability distribution of the location of a random walker on the vertices on the graph, then X prime X X times P times T is this is probability distribution of the walker after T steps. So this is quite interesting approach. So now let me recall the paper of 2003 of Kusaka and Suzuki. They're choosing the lattice. We consider the cellular automation, which is defined by UN plus 1 is Laplacian of UN, and UN equals B. B is the initial distribution. Here UN is 0, 1 value function on cells, and the Laplacian is given by U of P is sigma over UP, where UP is one of the neighborhoods. And here you take the distance, a difference between U of G minus U of P. So you take, for example, depending on which neighborhood you're taking, I'm going to show you an example how it works. So you set some initial conditions, you put some data, you put some, this is the lattice, most values are 0, f of p is 0 except 1, and these are marked by some color, let's see, blue. Okay, and then here we obtained Sierpiński neighborhood, through the iteration, through the process of discrete Laplacian, the Laplacians. And let's have a look at the first steps, for example. Here, supposing we are here. So what is the next, what will be the next? If you consider, for example, this point, this cell, and your neighborhood is Sierpiński, so it means you care for these 3 guys. So caring for these, you're adding them, and you have 1 minus 0. 0 is at the moment, so so this becomes 1. So next iteration we have 1. If we are getting here, if you're, for example, here at this point, then this is the neighborhood you consider, but in this neighborhood you only take these 3, so, because you're in Sierpiński neighborhood. So practically it remains 0, right? And if you are here, then this sum gives you 1. Okay, minus 0 is 1, so it's getting for 1. Okay, and in this way the whole figure grows somehow. And Neumann neighborhood, and that's the thing, produced, for example, such beautiful designs of folk serviettes, which you might have seen produced by ladies from the country. Mm. Okay. I've seen many iterations and many of these. I went through many simulations, and quite often the pictures which were produced by the discrete Laplacians were absolutely beautiful and amazing. I was wondering what culture is producing this. Sometimes it was like Aztec paintings or Aztec style, or sometimes it was some a Christian style, some very, very different things. I was wondering, how can I find the key? I believe that every culture has its own style. Maybe it can be found, described by some Laplacians. Here is more neighborhoods. This is the most closer case to the basic definition on the graphs. As you remember, you sum up over all the neighbors, nearest neighbors, right? So this is, you take all the nearest neighbors, and well, one of the iterations produces this. Okay, and also in that paper it was mentioned that we can give several realizations of evolutions which are given by the iteration dynamics of discrete Laplacian operators. Designs of carpet, crystals of water, flowers, doing designs of butterflies, and this all can be produced that way. Look at the carpets. Unbelievable, very, very, very beautiful. This is with use of more neighborhoods. Then you have crystals of water by hexagonal neighborhoods. And here we have flower patterns like these, many flower patterns, unbelievable number. And of course, many, many butterflies. I don't know if it's a butterfly, but perhaps Professor Suzuki would know better. I've never seen such a butterfly. Okay, so hexagonal neighborhood also this is one nice, very nice. Usually things which are similar to a hexagon-like figure. Okay, so we're going to practically go the same way, but we shall do some small modifications. Of course, we shall choose a lattice, a square lattice or hexagonal lattice. Now, the choice of space of not 0, 1 valued functions, but let us allow the functions be from values from 0 to some n, some finite number. Okay, in the past, so we start with 0, 1. So we put something on the table, some initial values, 0 or 1, but then. And we, of course, take again, we can have some evolutionary neighborhoods. Maybe they are interesting. Any other is interesting to consider as well. So we can have Moore or Neumann, diagonal Neumann, hexagonal, Sierpiński, Peano, Roof, Tenenbaum. I don't know what the name is called, Tenenbaum. This is Roof. Everybody can see it's Roof. Right. Here is some exotic name. Of course, if you are in hexagonal lattice, you can take. I didn't give the names, but this could be any. This looks like a boat, so I will show you the simulation for a boat. Of course, it doesn't have to be symmetrical along this horizontal axis. It can be asymmetrical. It can be anything. Okay, and so the definition remains as before. But now un is from 0 to k minus 1 valued function. And the value will be in the cell will be sum over the neighborhood between of differences u of g minus u of p. But you can quite often take modulo k addition. So no longer modulo 2. But modulo k. Okay. Practically, I was interested in the following scheme. If we take always 2, modulo 2, it will be the case which was considered in the previous paper. So this is more or less the same thing. But referring to this binary, ternary, binary, and binary, this is BTBB construction. Why don't we take modulo 2, modulo 3, modulo 2, modulo 2, and all around the same pattern. Of course, we can take 4 and 5 in this place anyway. Okay, so the general formula would be like that. So some k here. If you put a 3 in place of k, we are investigating the BTBB construction. Okay, and what is that? Oh, it's the last slide. It's time to show something. So I would like to show the results of my computer simulation. So diagonal Neumann goes like this. We started with this tiny thing. This is the 2-2-2-2 scheme. So it seems nothing is going on, but you can notice that from some construction is being done, but after some time, everything disappears. Or like now, we just obtain many new seeds, the same seeds, and construction is being done. Here is the BTBB construction. So it becomes that it seems that everything is more dense and the distances between dots never vanishes, right? It always grows and grows. Here is 2-4-2-2. And again, it's growing. Ah, disappeared. It's quite big. Oh, disappeared.
Oh.
Yeah.
Ah.
And disappeared. Now
Wow.
it's 5. Let's see what happens with the get 5. So 5 again is quite positive, right? But well, well. Okay, and 6 again will be let's see if 7 is good. So far, it seems that 3 and 5 give the least repetitive patterns. Oh, I don't know what's next. It's interesting if they will glue or not, but probably not. Right? Okay, so let's see the more. Yeah, it's time for more. Okay, is the this is first 2-2-2-2. Oh, how beautiful, how big. Oh, and return to the initial point. It's like a soap bubble. Okay, now we have the 2-3-2-2. And look what is happening. Looks interesting, right?
Oh.
Uh-huh.
No decomposition. Oh. Oh. Fine.
Okay.
Oh.
This is 4. Oh, this is 4. And the bubble. Yeah. So again, 3 was very creative.
Oh.
5 is also good. 5 is.
Polityk taki się zachowuje, jaki dziadku. Podziwia jakby. Podziwia tutaj wyniki na komputerze.
Was disappointing. Wasn't so good. Now it's 6. Oh, it's probably 5 now. It's, oh, sorry. That was a wrong label there.
Oh.
5. This is 5, yeah. Ah, yes, that's, well, is it impressive? And one more about something on hexagonal lattice. I called it a boat.
Oh.
But still, the boats remain and remain. Okay.
What is that?
This is 2, 3.
2, 3, 2, 2. Oh.
It's quite dense, isn't it?
Not decompose.
And the boats never return.
Oh. Oh.
Yeah. To 4. This is 2, 4. So they grow and then, oops, something was wrong with the video. Well, with the video. Now it's 5. Let's see if it produces something nice. So 5 again is producing something very,
Does not decompose.
yeah. And 6.
Ah, 6. Eh?
Oh. This program did some mistakes in rendering. Oh. And again, the same patterns from the beginning. And 7. Kind of a frog or something, right?
Yeah.
So 8, nothing special again, right? Grows and disappears.
Ah, okay.
Yeah. Okay, so you can see, oh, let me stop that. You have seen that already. Okay, so this is what I wanted to show you. I hope it is somehow inspiring. There are more questions. Why exactly number 3 is so special here in this sequence, and also 5 and 7, but all the others are not and have the same repetitive disappearing manner. Thank you.
Thank you very much.
It was a pleasure to listen to your talk and watch the slideshow, of course. Okay.
Fine.
If there are any questions or remarks.
Jarek Duda has a questions or comments. Dr. Jarek Duda, you make some comments on the chat. Could you share with
Yes,
us?
so this is a small comment that there is this nice article I posted there. But there are some alternative Laplacians. So, for example, the Laplacian is based on thinking in one step, and you can do Merv-based Laplacian which thinks in the space of paths. It looks a bit it looks a bit different, but maybe it's worth to experiment here. To these different Laplacians, so they probably have different properties, especially from non-homogeneous situation.
Maybe can you share a screen with us, because you have two nice comments. Can you show us this?
So here are some Laplacians from these papers. So standard Laplacian is this one, yes, and here is based on the Merv. So you need to find the dominant eigenvector of adjacency matrix. This is psi, dominant eigenvector of adjacency matrix, and this is the Laplacian, and it should have different properties. So in this paper, they claim that for the link prediction problem, that using the Merv-based Laplacians, they get much better agreement with data for various approaches. And so here is a simple difference. So there is this sim rank to compare similarity between two vertices of a graph. It is done in a recursive way, that we say that it is average over the neighbors of similarities. What we convert to some measure, and it can be seen as going from random walk, so that we have two walkers from A and B, and we make random walk and wait when they will meet, and then calculate the expected value of some function based on this length. So this is for standard random walk, but they replace it with maximal type random walk and getting this a bit different formula based on this dominant eigenvector. So and they claim getting much better behavior for link prediction and other problems because of thinking in the space of paths, not single steps. So it might be valuable to experiment with them.
Can you show us this last Wolfram simulation? Can you just share the screen and show us this last simulation you pointed out on the chat?
Okay, so let me find it.
Małgosia, can you unshare, and
yes, I can.
Jarek can show it?
So the Wolfram simulation. So maybe let me put it in the chat. Okay, so here is them. The community. Okay, so stop share. Okay, so.
Okay.
Let me. Okay, so. More share screen. Okay, so okay, so here is really simulator. That's completely different behavior. That if having standard random walk and Merv, this is completely different behavior for non-homogeneous situation. So like I have commented in this talk about this random walk diffusion of the vertices. That the difference is, for example, in the boundary conditions. That classically the classical diffusion has uniform distribution near the boundary conditions, while Merv and quantum mechanics has reduced probability because the space of paths is much reduced there. So then is one there is this repulsion from boundaries. From the other side, if you have that defects, also there is very strong repulsion from this defect, finally leading to this localization. Anderson, like in quantum mechanics. So. And just some interesting fact that maybe it's worth to experiment with this kind of Laplacians to get, for example, this kind of behavior like you get.
Yeah, very, very interesting.
Thank you.
Well,
thank you. Good.
I have one comment on the presentation. So I would like to ask to Małgorzata about. So I see that to some extent, your simulations are a bit similar to crystal growth, right? And in crystal growth, you have what defines crystal is at some point not always there is potential that has some dependence on direction. So like you try to grow the crystal, so somehow your systems, at least some subset of your cases shown by you might be at least possibly formally classified as the case of growing crystal. That's so maybe even there is a kind of Hamiltonian dynamics that does describe it. So that's my first kind of comment. And second comment is that actually yesterday I gave a talk about classical and quantum Conway game of life. And I also have a little bit, not the same obviously, but similar patterns, emerging patterns of cellular automata. And actually I was able to describe or to parameterize the system of Conway game of life, stochastic Conway game of life, by means of Hamiltonians, quantum mechanics Hamiltonians, but with dissipation, with complex value potential. So my kind of hidden hypothesis after watching your presentation, after listening to your presentation, is that perhaps there exists a family of Hamiltonians that, so if you try to, because you have like so far sharp logic, but if you fuse logic a little bit, perhaps there exists a family of Hamiltonians, like dissipative non-Hermitian Hamiltonians, that carries out similar or the same sometimes dynamics. So that's just open hypothesis, at least just come to my mind after your nice presentation. So that's my comment. Or you have any view on that?
No, it's interesting. It's worth thinking.
May I make a comment, sir?
Sure, please.
Oh, I would like to say, Professor Novak, thank you very much for improving our discrete Laplacian. I have tried to computer simulation just about 20 years ago or so, and just I enjoyed it, and so it's very, very interesting because many kind of phenomena can be realized. For example, the carpet of Iranian carpets, almost of them can be realized by our simulations.
Yeah.
Or also
surprising.
butterflies appear, and the biologists have a strong interest in realization of butterfly, and so it's very, very interesting, and but just childish interest. But today you have considered BTBB structure. You have introduction to the BTBB structure, and then BTBB structure has some special properties in your simulation. Yeah. For example, 2222 is grow, but split. It means that the cell decomposition, same one with decomposition. But 2322 is more what they say organic, and so yeah, we can also
organized.
Yeah. So I have told the BTBB structure just fitting the phenomena, and this is a quark okay, and others okay, and etc. But if based on your computer simulation, we can make some mathematical theory of evolution. Then it's a theoretical one, not children's baby play. So I hope you can develop much more good, interesting examples, and so I hope you will work in the future. Thank you.
Thank you.
Thank you.
Thank you.
Are there any other questions or remarks?
I have one remark.
Okay, yes, please.
If possible. Cosmological observations didn't confirm discrete structure of space should influence propagation
could you-
of light.
Excuse me, could you repeat your question because there was some problem with connection?
Please say.
I would like to remark about hypothesis about discrete structures of space. Space-time, our universe, in minus 35 meter. This hypothesis originated from loop quantum gravity, as told Małgorzata. And recent large-scale observations, which have cosmological meaning, didn't confirm this discrete structure, because discrete structures should influence on propagation of life during very big distances, and this effect didn't was discovered. So it seems that the space-time is continuous in smallest scales, not discrete. This is nowadays situation, in my opinion. Maybe in future the situation will change.
Mhm.
Okay, so any other questions or remarks? If not, then let's thank again to the speaker.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you for listening.
So I think this is